Welcome back, everybody. So let's move on to the next lecture on syntax. So here's an intro. You remember these fundamental data shapes, right? We have trees, we have graphs, we have cubes, we have tables, and we have unstructured data, right? And now I'm going to share with you, I'm considering adding a sixth one because now it's becoming too much of a buzzword to ignore, but I need to see if the hype comes down. That would be vectors, collections of vectors, vector databases. But anyway, for the purpose of the lecture, we brushed up on tables at the beginning of the semester. And for lots of this course, we are going to focus on trees, right? But I want to tell you a bit more about why trees. Why are trees so interesting in the context of big data? So this is where we are. This is the technology stack. We are done with storage. Now we know where to store data that is large. We can store it on Amazon S3, on Google Cloud Storage, on Amazon Blob Storage, Azure Blob Storage, sorry. But we need to know what to store in there, right? Because for now, we just know we can store objects or files that are just bits, right? So what does these bits then look like? So today we are going to go on a higher level and talk about encoding and syntax. Encoding very briefly and then syntax a bit more. So syntax is about how to turn data into a text representation, just characters, letters. So there's many different syntaxes. I'm pretty sure everybody knows about CSV. Who knows about CSV? Okay, you go to any website, like, I don't know, the Federal Office for Statistics, and you can download pretty much anything in CSV. This is one of those. And then you probably also heard of XML and JSON, which are alternate syntaxes. RDF would be for graphs, Turtle also for graphs, XBRL for cubes. This will be less the focus of the lecture, right? Who heard of XML and JSON? Oh, this is fantastic. Okay, so you'll know a little bit about that. So we just dig a bit deeper. Now, something important is that on the level of S3 or Azure Blob Storage or HDFS, we store bits, ones and zeros. Now, you can store a lot of things as bits. And I told you, for example, videos, pictures, and so on. But for data, we love to exchange it as text in a text format, actual letters of the alphabet and symbols. One of the reasons is that a human can look at it and understand, right? We'll see later in the lecture that it doesn't have to be text. You can also store data in a binary form, and we will see that it has advantages. But we'll focus on data in a text form for today. Now, if we want to store text, we need to encode it into zeros and ones. So how is that done? I'm assuming a lot of you are familiar, but I just want to make sure that everybody is on the same page. So the characters are letters like A, B, C, D, uppercase, lowercase, the digits, the dot, the dash, the semicolon, and so on. How do you turn that into zeros and ones? Well, in the very early days of computers, the first way to do that was called ASCII. Who heard of ASCII? Okay, so ASCII has the idea that you have a catalog of symbols, in that case 128 for ASCII, and every one of these characters gets some number. You count them. This is the first, this is the second, this is the third, and you have a number between 0 and 127. We love starting to count at 0 in computer science. And what we got was a table like this. This is actually on purpose taken, looks like archaeology, right? But very old documents, where you can see it goes like this is 0, 0, 0, 1, 2, 3, 4, 5, all the way to 16, 70, 33, and so on and so on. It goes like this all the way to 127, right? Now, how do you encode numbers in zeros and ones? Well, it's only a matter of convention, because you know, since primary school, we count in base 10. We have 10 fingers, so we have 10 digits. But you know that base 10 is completely arbitrary, right? We could also have had base 12. Actually, base 12 was popular, right? When you count eggs, for example, in dozens. Well, one of the bases we could take is base 2. So we can also express numbers in base 2 just with zeros and ones. And this is what you get in here, where you have every number between 0 and 127 can be expressed with 7 bits. So these are the first three, and these are the last four. And whenever, for example, this 4 here would be 0, 1, 1 followed by 0, 1, 0, right? So 0, 1, 1, 0, 1, 0, 0 encodes 4. So now you have a mapping. Every character here can just be encoded into zeros and ones in that way, and it goes in both directions. You can write or you can read. So that solves the problem, right? Now we can have text, and we know how to store it as zeros and ones and to read it back to letters. Now there's a few more that arrived later. Why? Because ASCII was specific to English, and you know that in English we don't have accents or any complicated characters. There used to be some, but somehow they disappeared in the 19th century. But we do have special characters in Schweizerdeutsch, for example, a lot of them, especially if you use the spellings that use also these acutes and so on, all the accents. The problem is that there are so many languages in the world and so many different accents you can have that everybody developed their own encoding. So ISO Latin 1, also known as ISO 88591, is for Western Europe. But there was yet another one for, I don't know, Eastern Europe, China, India, and so on. And at some point, we needed to unify all of this, because that just couldn't be that we have all of these separate ways of encoding. And there came Unicode. Unicode is an absolutely gigantic catalog of symbols that all assigns, every symbol gets a number, basically. An encoding of Unicode is UTF-8 and UTF-16, right? These are possible ways of put that into zeros and ones. Unicode now is pretty much done in the sense that almost all the languages in the world have the symbols encoded in there. So that now the working group is mostly focusing on emojis. Like every time Unicode is updated, you get new emojis, and that's actually very useful. But what I want to say is that for the alphabets, that's kind of taken care of. All right? And this is just an example. You don't really have to worry for the purpose of the lecture. This is just to show you that unlike ASCII, where it's always going to be 7 bits, plus maybe a 0 in front to make it 8. But in the case of UTF-8, it's elastic, it's magic. If it's a character like from English, then it's going to fit on 8 bits. If it's a slightly more complicated character, like, I don't know, Greek letters in math, that fits on 16 bits, always a multiple of 8. And if it's a more recent symbol, like the euro symbol, which is just a few decades old, then you will need, in that case, 24 bits, right? So it's elastic automatically, right? You don't need to understand the details. This is just that there is a way, based on the number that it has in the Unicode catalog, you can automatically map it to these zeros and ones. So all you need to know is that you can map it and you can read back the symbol. All right. By the way, who already experienced that you try to open a file that contains a umlaut, o umlaut, u umlaut, and you try, I don't know, to import the CSV in Excel or LibreOffice, and then you notice that instead of the umlaut, you get weird symbols like square root and so on. Who saw that? Okay. That's because of the encoding right here. Basically means that it's encoded maybe in UTF-8 and you try to open it with ISO Latin 1. So the decoding with the zeros and ones is basically incorrect. This is where it's from. Now you know that this is the reason. Okay. So now we've solved the problem. We know how to store letters and digits and symbols as zeros and ones. So now we can forget about the zeros and ones and reason one level higher with characters and letters and symbols. Okay. So CSV, you already know. I'm going to start from there. CSV is basically a text representation of tables, right? Comma separated. Every comma basically separates the cells. On the first line, typically you have the headers, which are the name of the columns. And then on every line, you have one row, one record, one business object, if you remember. So in that case, there are 2 business objects, 1 and 2, that I put in there. Okay, 3 columns, 2 rows. I hope this is clear to everybody, right? The mapping between CSV and the table. So you see that here, the idea is that we have something that is technically logical as part of a data model with rows and columns. You know, you could almost treat it mathematically, but we represent it as text. ID, comma, LAST, space, and this is text, right? But this is a textual representation of the table. Now, as a word of warning, if I just show you this, it looks like CSV is extremely simple. Be careful, CSV is extraordinarily complicated. And the reason it is complicated is that there are so many different conventions in how to write CSV that every time you want to open a CSV file, you need to first tell how to open it. For example, you could use commas, but some people use tabs or semicolons as separators or spaces. Then there is the question of what do you do if you have a comma that is inside an actual string, like for example, general special relativity. Here there is a comma, but I don't want that comma to be interpreted as the separation of a cell. It's actually part of the text. So what you do, you put quotes around it, and the quotes tell you, okay, that comma is special. The comma inside the quotes is not a separator; it's really a real comma. But then what happens if you have quotes inside, like on row 2, now you have quotes. So what do you do? Because the quotes should not be recognized as quotes of CSV, but actual quotes that go in there. So what do? You triple the quotes. Sorry, you double the quotes. So you have an opening quote in there, a double quote that means it's an actual quote, then incompleteness, then a double quote meaning it's an actual quote symbol, and so on. So you see, it's complex. And there are so many conventions. There are other ways than the double quote. Some people prefer to use backslashes, and so on. So there is an RFC called RFC, Request for Comments 4880. It's one of the places where you have a lot of standards, RFC. The problem is that in practice, everybody does a little bit what they want. And so it requires a bit of effort to basically open the CSV files. Who's already been through that, trying to open a CSV file and having to deal with all of that? Okay, so you have a bit of experience with that. Okay. So now CSV is for tables. Now in the first week of the course, I told you about these normal forms, right? Some of you already knew because you attended Information Systems for Engineers. Some others got scared, probably like, what are normal forms and why suddenly am I throwing at you all these normal forms in the first week? Basically, a normal form is, the idea is simple. The idea is that first, you don't want tables in tables in tables in tables. You want everything to be flat. That's the first normal form. And for the higher normal form, you basically want to have a lot of tables that each do one thing rather than a gigantic table that tries to do everything, right? For example, you want to have a separate table for students, a separate table for courses, a separate table for rooms, and so on and so on. Then you can say you're in high normal form, right? If you're in low normal form, imagine that at ETH, the database was stored in a single giant relational table that has everything, the lectures, the students, and so on. That would be very, very hard to manage and to modify every day. So there are many normal forms, and one of them is called Boyce chord. There is the second, the third, the fourth, and so on. So there's many of them. But I have good news, because as I told you in the first week, we're going to throw them away. It means that for the purpose of this course, we don't really care about having many different tables and each table does its thing. We will not even care having flat tables. We will even accept tables in tables in tables in tables. That's going to be fine with us. So the first, second, and third normal forms and the Boyce chord normal form, they all go right there for the purpose of that lecture. Why? Of course, I need to tell you why, right? There is a reason for that. It's because in this lecture for big data, we want to analyze data. So typically, when you analyze data, you connect to the internet, you log on to a website, and you download a data set, and then you analyze that data set. You don't actually want to modify the data sets or to update anything. You just take it as it is, and then you analyze it. This is very different from having a relational database behind a web shop where the people are shopping, and they update their shopping carts, and they place orders, and so on. So here, the data keeps changing, but not in big data. Here, we just download the data set and don't touch it. And the idea is that the reason we want the normal forms in a web shop, for example, is because we write a lot. And when you write a lot to the data, you really want to spread it across plenty of tables that are flat. So if it's write intensive, to avoid these ugly things called update anomalies, inconsistencies, and so on. But since in our case, all we want to do is download a data set and analyze it, maybe in Jupyter Notebooks, it's read intensive. So in that case, we don't even need to care about normal forms. We can denormalize. We can have a single big table instead of smaller ones. We can have tables in tables. And the reason is we avoid joins, because again, if everything is in the same table, then I don't need to join anymore. It's already joined. It's already joined into a single table. Who has the intuition of that? Okay, so normal forms, go to the trash can, and we are going to have a lot of single data sets like this. Visually, it looks like this. This is a beautiful relational database, all flat, divided in multiple tables. So this is a high normal form, right? You have a table for products, table for sales, table customers, high normal form. If we denormalize, it means we do that. We just merge it back into a single table because we just want to analyze the data. What you do is actually join. You get that by joining these two into a single table. But what's new in big data is that this is what we're actually going to store on S3 or HDFS. We will store that and not that. That we throw away, we only store that. So this is a table. It turns out to be flat, but as you will see, it will not always be flat. A table you can see as a collection of rows, right? If you have a collection of people, one person on every row. So a table is a collection of rows. An alternate terminology is collection of tuples, right? Every record in my table is a tuple. Now, if I take one tuple, one row, I marked it in green in here, phone 800, John 1. What is that mathematically? Well, mathematically, it's a function, a partial function, a mapping that maps product to phone, price to 800, customer to John, and quantity 1, right? It's just the header. The product is a phone, the price is 800, and so on. So mathematically, you can represent it with this symbol that is for the functions, right? This is the product is mapped to phone, price is mapped to 800. S, I use, it's my convention for the set of strings. So this is all the possible attributes that you can have here, 4 columns. And V is the set of values. That's also my convention. It's not universal. So we map the headers right here in purple to values right here in green. And of course, if I change the row and I consider the other rows, that will be the same, but here the values will be different. Who is with me? Right? So every row in here is a tuple that looks like this. So that's how the mathematicians would represent this. But we are computer scientists, and we prefer to look at it this way. Do you see it's the same thing? It's exactly the same thing. It's just written in a different form. In fact, it's even text. It's a text form. And now you see that I have the quotes around them, but the product is phone, the price is 800, the customer is John, the quantity is 1. This text is called, you know, right? It's called JSON. I heard it. So this is indeed the JSON syntax, right? You might have seen it before. So the JSON syntax is just a textual representation for tuples, right? So instead of looking at it with the mathematical scary notations like this, we just represent it as a text document that looks like this. That's JSON. Now, just so you know, if you look at that text, you will see that I did a lot of nice things in there. For example, I put 1 on every line, and then I have a small indentation in there to make it look nice. Why did I do it? Just because I'm a human being, you're human beings, and it's easier for human beings to have it nicely formatted like that. It's like when you write a formal letter, and you just make sure that the paragraphs are aligned and so on. But this is really just for us as humans. It's just to make it beautiful. In practice, you don't have to. I could also have it all on the same line like this, without new lines, without indents, and that's just fine. It's the same thing. And in fact, typically, if you want to create one such, that's called an object, right? One for that record, one other for that record, one other for that record, so 6 of them, you can basically just line them up like this. So here I put the first 5. I don't know why I might as well have put the 6th one, but for some reason I put 3 dots. But anyway, you see, every one of these objects corresponds to a different row in there. Who sees that it's the same data? Okay, but in one case I have a table. I could also have stored it as CSV, but instead of storing it as CSV, I store it as JSON, CSV. But just like CSV, it's in fact text. Okay. Now, even though it's not in the high normal form, this table still fulfills my 3 criteria: domain integrity, relational integrity, and atomic integrity. Atomic integrity because there is no table in the table, it's all flat. Domain integrity because if you look at the columns, they all look nice. In the first columns, you have strings. In the second columns, you have numbers, and so on, right? So this is domain integrity. And relational integrity because it's a table, right? It doesn't have missing cells or extra cells. So you see that in that case, I check all the boxes. I am in the beautiful and marvelous world of SQL, which we studied in information systems for engineers. But as I told you, we are going to now venture out of that territory and start dropping all of these. And that's called NoSQL for not only SQL. And what's going to happen is that we are going to now break the rules and throw away the normal forms. So you know the first normal form says it has to be flat. I cannot have a table in a table in the table. Let's throw that away and allow for tables to be in tables. That's going to be fine with us now, right? So this goes there. So now this is what I get. If I put tables in tables, I might get something like that, right? So if you did that in a bachelor's lecture of databases, people would scream at you like, no, you can't do that. This is not in the first normal form. Here we can, right? It's big data, so we are allowed to do that. So I can put a table in a table in a table. This is called nestedness, okay? So that's the first thing that we can do in big data. Now, how do I represent this in JSON? Well, what I can tell you is that in CSV, you can't. In CSV, it will not work, but in JSON, you can. And in fact, the way you do it, let's take this is how many records are there? There is one record, a second record, and a third record, right? And you have tables inside, but it's still 1, 2, 3 records. Let's take the first record, just the first one. What does it look like in JSON? Well, you probably guessed, right? This is the easy part. Product, phone, price 800, orders. What do? It's a nested table, no problem. In JSON, we have this angle brackets here that says it's a list, so-called an array, a list. And inside, if I map this to JSON, that we know how to do. Customer John, quantity 1, here it is. Customer Peter, quantity 2, here it is. Customer Mary, quantity 1, here it is. We put commas to nicely separate them and put them inside. So you see that in JSON, I can have a table in a table. Who sees that? Right? This is magic. I cannot do it in CSV, but in JSON, I can do that. Now, here are some other rules we can break. Relational integrity. How do we break it? Maybe by removing cells, right? And here I removed one. Did you see the one I removed? I removed that cell right there. It went away. We don't have relational integrity in there. That's no longer a table. It's some thing that looks like a table, but it's missing a cell in there, right? And that's fine. In big data, it's fine. This is called heterogeneity. How do you see it in JSON? Well, it's simple. In that case, you have customer Mary, and for quantity, you just don't have anything. In CSV, you could not do it. Well, you could kind of leave it empty between two commas, but it's less nice, right? So you see that with JSON, I can account for nestedness. I can have a table in a table, and I can also allow for heterogeneity. If I have a missing value, then I just leave it out in the syntax, okay? So what we call data denormalization is pretty much that. It's breaking rules and throwing away the normal forms. So it means that we go from this 1970s way of doing relational databases. It's flat, it's homogeneous, relational integrity, domain integrity, atomic integrity. And if we throw these rules, then a lot of things can happen. We can have tables in tables in tables. We can have extra values that come out of nowhere. We can have missing values. We could have invalid values. Maybe we have integers everywhere and a string in here and another nested table in there. It's nested and heterogeneous, right? SQL, NoSQL. Who is with me? Okay, good. So now, this is an example of a table. I can have some nulls in there, but it's still kind of considered a table. And now I have this other collection that breaks the rules. I have tables in a table. I have missing values and so on. Here and here it's missing. And if you look at here and here, this is the JSON representation of this. And this is the JSON representation of this. Who agrees? Right? It's intuitive. It's exactly the same idea as before. Whenever you want to nest a table, you need these, it's called angle brackets. These are called curly brackets, and these are called, sorry, not angle, what am I saying? Square brackets, the square brackets and the curly brackets. All right, so you see that we are moving away from tables as homogeneous collections of flat items, flat records, and we move away to heterogeneous collections of arborescent items. Arborescent, if you don't speak a Latin language, it means like a tree, like arbre means tree. Okay, and this is called semi-structured data. On the left, you have relational data. On the right, you have semi-structured data. And this is a whole spectrum. You basically have on the left the fully structured data that fits in tables that strictly respect the normal forms. On the right, you have data with no structure at all. And here you really can imagine ChatGPT analyzing text from Wikipedia, right? So that's totally unstructured. And somewhere in the middle, you have this semi-structured data. It's kind of unstructured because it's just text. But if you look closer, it's not text like English. It actually does have some structure. This is why it's called semi-structured. Okay. Now, a second aspect of the syntax that we are looking at today is that it is standardized. It is standardized by W3C for XML. That's the same standardization body that also standardizes HTTP, HTML, and so on. And ECMA standardizes JSON, right? And it's the same that also standardizes JavaScript, ECMA. Okay. So now let's start diving into it, right? What I gave you until now was a motivation, like why do we have syntax and why do we need something else than CSV? It's in order to account for data that is denormalized. So what is syntax? Well, when you have a syntax, like XML or JSON, you're basically asking a yes-no question. So I'm giving to you some text documents. You can download it from somewhere. And the yes-no question I can ask you is that text JSON? More precisely, I will ask, is that text well-formed JSON? And then there are two answers. It's either yes or no. I can ask the same question with XML. Is this text that I gave you well-formed XML? The answer is either yes or no. And I want to give you today the intuition of that with your eyes, you can see if it's well-formed or not. Of course, in practice, it's fully automated. You can just feed it into some program that will answer. This is what computer scientists call a language. A language is just a set of text documents or a set of strings that is considered valid for the language. But I'm not going to be using the word valid. I'm using the word well-formed. You will understand why in a few weeks. Okay? So yes, no. Now I'm throwing at you an example of XML documents. Who already saw one before? You actually saw one in the previous hour at the very end of HDFS. I show you configuration files of HDFS. They were actually also XML. So this is one of the two syntaxes. And the other one is JSON. Now this should be more familiar to you because I showed you the example on the denormalized data. Who was already familiar with JSON before? Okay, several of you. But I'm going to now go into the details and teach this to you, right? Okay, XML, JSON, XML, JSON. So I'll start with the easy one. I mean, JSON has the reputation of being easier than XML. In general, you really need to try to not have any bias towards the one or the other, because really there are two different syntaxes. They all have strengths and weaknesses. In practice, it's good to know both because both are used in practice. So let's start with JSON again, because this one is easier to learn. So what do we have in JSON? The way I'm going to show you the languages is that it's like a Lego game. I'm going to give you the building blocks. Like in the Lego game, you might have the red brick of 1x4 and so on, right? So I'm going to give you the building blocks. So in JSON, there are 6 building blocks, 6, exactly 6. This is the first one. So the first building block is a string. A string, I assume all of you or most of you are familiar with that. It's just a sequence of characters, a sequence of symbols, and computer scientists put double quotes on both sides to delimit them. So the first string is foo with FOO. And then you see what happens with the second string. It looks a bit weird. This is because there's this backslash here. And whenever you have a backslash followed by an N, that actually is a new line. It's just an escaping sequence for a new line. And here, this is an escaping symbol, backslash U, for a special character. guess what you put in there? It's the Unicode number. I told you about Unicode, right? This huge catalog of letters and symbols and emojis. You can even put emojis in JSON. You just need to know in base 16 the number of the character you want to put. So this is extremely powerful because you can put any symbol, any emoji, any character, can be Arabic, Japanese, and so on and so on. Any symbol you want in there with the Unicode character. So this is the string. That's the first building block, double quotes on both sides. The second building block is numbers. It's a bunch of digits, possibly followed by a decimal period, possibly followed by more digits, and then possibly followed by E, which is times 10 to the power of, right, the scientific notation, and then plus or minus, and then again digits, right? So E plus 5 really means times 10 to the power of 5. It's the scientific notation. And this is it. So in JSON, you can have numbers like this. What's really nice is that there is absolutely no limitation. If you want to put 1,000 digits, you can go ahead and do it. Technically, it's also well-formed JSON, right? So you can have integers, you can have any decimal number, right? Any decimal number can be expressed in this way. Okay, so this is called numbers. That's the second building block. Then we have Booleans. That is easy. There's only two. There's true and then false. That's basically the notion of logic, right? A statement can be true or it can be false. We also call them flags in some configuration files. True and false. There is no quotes around true and false. Just true, just false, without quotes. And there is a fourth one that's null. It's a bit like the SQL null. Null can appear explicitly in the JSON documents, and it just means that you don't know the value or you don't want to tell the value or for various reasons, right? It's just a null. You can also think it's kind of the same thing as a null in Java, in C++, so you'll probably be familiar. So we already have 4 building blocks. These 4 building blocks have in common that they're atomic, right? They are just what you could have them technically in the cell of a table, these 4. In addition to these 4, there are 2 additional building blocks, but these are not atomic. These are called structured. The first one is, it's on track, a bit slower today. I need to click again. There you go. So the first one is the array. It's just a list of values. How do you recognize an array? Because of the square brackets. You see on the top of and the bottom, it's just the square brackets. This is an opening square bracket. This is a closing square bracket. And then you could put any values you want. Here, there's a number, there's a Boolean, there's a string, there's a null, there's an object. It's on the next slide, comma, separated. This is an array. The order is important in there. There is an order in the array. It's an ordered list. And finally, the objects. The objects, you can really consider them just like the tuples in a table, right? Every row in a table associates an attribute with a value. That's exactly what objects do. So foo, bar, str would be the attributes. And then on the right, you have the values. So you see foo is a number, bar is a Boolean, str is a string, obj is an object, and q is null. And you see the difference with arrays because you have curly braces. This is called a curly brace, opening and closing, and you also need the commas to separate them. And here you see the colons that separate what is called here a key and what is called a value, right? Remember how I told you can say block, chunk, split, partition, shard, and so on? It's the same thing here. There are people who call these keys. Some other people call them fields. Some other people call them properties. You know, just be aware that there's many ways you can call them. Typically in JSON, it's called a key and a value. So that's 6 strings, numbers, Booleans, null, arrays, objects, and that's it. That's all of JSON. So now just a few more considerations in order to say if yes or no a document is JSON. There are a couple of things you cannot do. For example, the key must be a string in an object. So what you see here is an object, but the key is not a string in quotes. That's not okay. That is not correct JSON. That's wrong. You cannot do that. Here, you're missing the quotes. That's also wrong. This is fine. Next, this here, let me put it that way. For the purpose of the course, it's not okay. You cannot have twice the same key. Why? Well, imagine a table with two columns the same, right? If you have a relational table, every column name must be different. So if you have twice the same key in the same object, that's not okay, right? You have a collision between the two. This is fine because the keys are different in the same object. Now, those who know JSON and the purists might say, yes, 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 but actually, if you look at the spec, technically the RFC, the original one, it doesn't say that it's forbidden. It just says you should not be doing it. There is something that computer scientists like to do is that whenever you should not do something, then you treat it as you must not do something. It's called also treating a warning as an error. It's just safer, right? You know that everybody will be able to read it. So technically, JSON would not strictly forbid repeating a key, but if you do that, you should expect that maybe 90% or more of the software that can consume JSON will refuse it. That's basically what happens. So for the purpose of the course, and because it's used for data sets and it's mapped to relational table, we treat this warning as an error, and we are not allowed to repeat the same name of the key in the same object. We cannot have twice the same key. All right? Okay. Now, I told you that we can use JSON to store data. I gave you the example with the table. This is a real-life example. That's called the Great Language Game. It was played, I think now it's quite old, maybe 10 years ago. Whoever heard of that? It was a website that you could connect to. You did not even need an account. You just connected to it. And it would just play audio, somebody speaking. And then it would tell you, okay, that person speaking. Did they speak Chinese, German, Italian, or English? Then you have to pick an answer. And then it's right or it's wrong, and then you accumulate a score. And basically, when they did that, so they put it online and have people play, it was actually quite fun. We even played it at the Polymensa, I remember, with our laptops a few years ago. And they recorded what people were doing. So they basically, every time somebody played the game, they created a JSON object that basically says that the audio played was Italian, and that's the code of the sample, just like a block ID in AGFS. The choices given to the player were Chinese, German, Italian, English, and the player guessed German. They were wrong, right? It was Italian. So they guessed German, and the answer was wrong. That game was played in 2018 on November 7th by somebody in Switzerland. Okay. And we have a data set. We actually have it for the lecture. You can download it. I think it has 16 million objects like that. 16 million. It's a few gigabytes. And we love to use it for the purpose of the course. It's relatively simple. You can understand it. It's just 16 million times something that looks like that. And you can query it and aggregate statistics on it, right? So that's called the Great Language Game. This is the example I showed you earlier, that any table technically can be converted like this. And what is typically done is that every bracket of the table gives you an object, and we like to put one object per line. This is called JSON lines, this format, where every line of your text file contains one JSON object. Now, again, I'm repeating here. I already showed that to you. So if you have a table in a table, all you need to do, now I can use the words of the terminology, because now that I have explained JSON, I can say it. This is an array that contains 3 objects, right? And an array of objects is typically what you use to have a table in a table, right? A nested table is basically an array of objects. Okay, who is with me? Okay. So this is JSON. It's relatively simple. And now I'm going to move on to the other one, XML. It's a bit complicated, more complicated. And in fact, that's the reason why I'm not going to show you the whole of XML, just a subset. Yes? Yes, absolutely. Yeah, you can have, you just have a square bracket with nothing inside. You open and close, and that's fine. That's an empty array. That's absolutely allowed. And then you have an empty table. Yeah. Mm-hmm. Okay. So XML. XML is extremely complex. I put a link to the specification of XML, but I think I stamped it as insanely optional because I don't want to scare you. I mean, you can try to open it, but at your own risks. I'm only going to give you a subset of that, the one that is actually useful for data and that it will allow you to understand data. Okay, the first thing I want to say, because you might have heard, okay, XML is old, XML is complex, who cares about XML? The research on XML has been done, it's now now it's the past. This is just not true. It might be done in academia. In academia, you will not find many people still working on XML. But if you go to companies or if you go to governments, XML is all over the place. A lot of government standards use XML. An example of that, and that's one of many examples, is that the banks can issue tax statements to file with the tax authority. And a couple of years ago, they introduced the notion of an electronic tax statement, right? An E-Steuerauszug. It's a barcode. You basically have a PDF. At the end, there's barcodes. And at the end, the barcode, in fact, contains, guess what? XML. It has XML inside. And that is a sample of that's taken from an official government website in Switzerland that shows an example of using XML for reporting data. As you can see, they have a very good sense of humor if you actually look at what's written in there. All right, or you can look offline. So what does XML look like? Well, just like JSON, I'm going to give you building blocks, right? JSON has building blocks, and so does XML. The first building block is called an element. An element is basically a zone delimiter. You basically have a start and an end. Just like when you arrive in a city, you get a shield that tells you this is the start of the city. And when you leave it, you have another shield that tells you this is the end of the city. So this is called an opening tag and a closing tag. And here you don't have square brackets or curly brackets, you have angle brackets, the third kind of brackets, right? Angle brackets, that's called an opening tag. And the closing tag is the same, but you have this extra slash, right? Now, just like the array could be empty, as you mentioned, that could be empty, that's fine. You just put whatever inside, could be empty. But if it's empty, computer scientists are so lazy, we love to actually save space. So if this is actually empty, we don't want to have the opening and the closing tag. We like to be lazy and to just use that empty tag with the slash at the end. It's just really a shortcut. That would have been fine too, right? But since we are lazy, we love to actually shorten it to this. Okay, so this is an element. Next week, I will give you the other building blocks, attributes, text, mainly, and I'll show you more XML. So this is it for this week. Thank you very much for your attention. I hope you enjoyed learning all of this. You will have the exercises this week on HDFS, also the quizzes released. For the exercises on the queries, by the way, you can check again if you didn't pass, maybe now you pass because we allowed a few more answers. For example, if you just added a space or you have quotes and so on, we also counted it as correct. So you can check again. Thank you very much. Enjoy the rest of your day. Thank you, Shajeng, for the moderation, and I'll see you next week at 8 a.m. Thank you very much.